Today we're going to be looking at some properties of exponents. We had a lot of properties of exponents before, and we're going to apply those same properties, but before our exponents were all whole numbers, like 2 or 3, and now our exponents can be fractions, as we learned about yesterday. The same properties apply in the same way, so we do the same type of thing. It's just going to have some fractions involved in it as well. So to review a couple of those properties that we learned before, if I have something like x squared times x cubed, I get x to the fifth. When we are multiplying bases, we add the exponents. Okay, so that's something that we learned before. That's true even if those exponents are fractions. Okay, we would still just add those up. If I have something like x squared to the third, I get x to the sixth. We multiply those exponents together. We had that before. It's going to be the same now. It's just going to have some fractions involved in it. And if I have something like x to the 8th over x to the 4th, I get x to the 4th. We subtract those exponents. Okay. Property we learned before, but today we're going to be doing it with some fractions in it. All right, so here the bases inside are different. 2 and 3 are different, so we can't combine those. Okay? If it was 2 to the 4th and another 2 to the 4th, then we could combine those by adding the exponents, like we just looked at a property. But when the bases are different, we cannot combine them. But there's a power on the outside of this thing. So when there's a power on the outside of it, we have to give it to each part inside, and what do we do with them? Multiply them. Power to a power, we multiply. So I'm going to have 2 to the 4 times 1/4 and 3 to the 4 times 1/4. Now you wouldn't have to write at this step when you're doing your work, but just to show and emphasize what we're doing here, I'm going to write that out. What is 4 times 1/4? 1. 1/4 of 4 is 1. So then I get 2 to the 1st times 3 to the 1st. Well, what is 2 to the 1st? 2, and 3 to the 1st is 3, so I get 6.
Wait, how do you multiply the fraction again?
Multiply the fractions, 4 times 1/4.
Like, yeah.
When you multiply a fraction, typically it's easier if they're maybe both fractions. So I put it over a whole number, and then you multiply straight across.
Oh, okay.
So 4 over 4, which is 1. Alright, so in this one we have a division, but the bases are different in there, a 12 and a 4, and so we cannot combine those. The bases have to be the same to be able to combine them, so we cannot combine those. But we do have a power on the outside, but we also have some powers on the inside, and those powers are all the same. Okay, there's 2 on the outside, they both have a 1/3 power on the inside. So what I'm going to do in this problem is kind of a little bit backwards of the last one. So in the last one we distributed in the power. On this one I kind of want to pull out the power. So I'm going to pull out that 1/3 power, and say it's 12 over 4, and take out that power of 1/3. There was already a 2 out there, and I'm taking out that power of 1/3. So now inside I have just plain numbers, 12 and 4, so I get what? 3. So we get 3 to the 2/3. This is an acceptable final answer, but to review a little bit about what we did yesterday in terms of powers and roots, what does a fraction exponent do? The top is the power, and the bottom is the root. So another way of answering this problem would be to say that it's the cubed root of 9. Okay. But you could just leave it at the fraction exponent as well. Right, we learned about simplifying square roots before. And we said when we simplify a square root, what we wanted to do was find a perfect square that divided into the number in the problem. So, for example, a little side note problem, not this one, but just a completely different problem that's related. If I wanted to simplify the square root of 27, I'd want to find a perfect square that goes into 27. So, what is a perfect square that goes into 27?
9.
9 times 3. And the square root of 9 is 3. So we get 3 squared to 3. Okay. Remember, in simplifying a root, our goal is to make the number underneath the root as small as possible. Try to take as much as possible outside. Well, when we're simplifying a square root, we're looking for a perfect square that goes into that number. So when we're simplifying a cube root, we would be looking for a perfect cube that goes into this number. A perfect cube is something times itself 3 times. So 2 cubed is 8. 8 does not divide into 54. 3 cubed is 27, and that does go into 54. So we're going to separate this out and make it cubed root of 27 times cubed root of 2. Same way we did for square roots, just now we're working with a cube root. What is the cubed root of 27? 3, because it's 3 times 3 times 3. Cubed root of 2 we can't do, so we just leave. Questions? Okay, warning, this is the longest type of problem, this problem. So before we go into that, I know we're all on the same page. You don't have to tell me when we're halfway through that this problem's long, because I know it is. So when we simplified square roots, as a side note, if I wanted to simplify the square root of a fraction, we separated and made the square root of the top and the bottom. Then I can do the square root of 4 is 2, but we have that square root on the bottom. And we said it's not considered appropriate to leave a square root on the bottom of a fraction. So how do we fix it?
Multiply by a flip square root and by square root. Yes.
You multiply by the square root, by the same square root. Because when you multiply a square root by itself, it just cancels out. But if I multiply the bottom by square root of 3, what do I have to do to the top? Multiply by the square root of 3, so I'm really only multiplying by 1. Because then I'm not changing the value of this problem. So then I get 2 square root of 3 over multiply a square root by itself, and we just get the number. Okay? So we've dealt with square roots before. Now we're going to deal with other roots. The properties are the same. It just takes a little bit more as these powers get higher. So we're still going to split this up into a root of the top and a root of the bottom, but it's a fifth root instead of a square root. Now if it takes 2 square roots to cancel, how many fifth roots do you think it takes to cancel?
2.
5. Okay, so if it takes 2 square roots to cancel, 2 is square. If it takes then 3 cube roots to cancel, okay, whatever type of root it is, it's going to take that many of them to cancel it. So, 2 ways of writing this. Long way is to write it out so that I have 5 of them. Okay, I only need 4 more because I already had 1. So now all together on the bottom there, I have 5 of the fifth roots of 4. Okay? That's the long way of writing it. You can do it that way. Some people, it helps you to actually see that there are 5 of them there. A shorter way of writing it, which is okay, but for me personally, especially as you're learning it, it's not my preferred way, just because it is a little bit harder to see. But another way of writing it would be to say, let's see, we got the fifth root of 3 over the fifth root of 4. would be to say, okay, I know I already have one fifth root of 4, so I need 4 more of them, and just do it like to the 4th power. Because that's the same thing, right? Writing it out 4 times or writing as a 4th power is the same thing. Just for me, especially as I'm like learning this, I think it's actually helpful to see all 5 of them there. But it takes more writing, so it's up to you. Okay, I'm gonna go with writing it out all the times. Alrighty. If I'm multiplying by all those on the bottom, what do I need to multiply by on the top? The same things. So that I'm really only multiplying by 1 each of these times. Alright, so now I want to multiply all this stuff together. So on the top, I've got a fifth root of, and I grab a calculator, and I'm going to multiply 3 and 4 4s together. And I get 768. On the bottom, when I multiply all that together, what do I get? 4. Okay, that's why we did this, because 5 of them will cancel each other out, and we just get left with whatever was underneath. Yes?
So you did the fifth root of 60?
Not 60, no.
You don't multiply them together?
On the top?
Yeah.
Yes, but I multiply 3 times 4 times 4 times 4 times 4, which is 768.
So you just leave the 5 there.
Yeah, the 5's just on the outside. That's the type of the root it is. Just like when we did a square root, we didn't do anything with the 2. We actually didn't even write the 2. But we just multiply out together all the stuff underneath.
Oh,
So
okay.
we multiply the 3, the 4, the 4, the 4, the 4, however many 4s are there. Okay. Right, and that 5 just stays on the outside. Then on the bottom, all those roots cancel each other because there's 5 of them, 5 fifth roots. Just becomes whatever was underneath. Now 768 is a pretty big number. That means this root probably simplifies. So in our last problem, we looked at simplifying a cube root, and we said we needed to find a perfect cube that divided into it. So if now we're working with a fifth root, we need to find a perfect fifth powered thing that goes into it. I don't expect you to know your fifth powered things. I don't know my fifth powered things. So then I just start trying them out and say, okay, 2 to the 5th is 32. Does 32 go into 768? I'm going to try that out on my calculator, and it does. Okay. So then, this becomes 32, and it's times 24. Okay. If I had tried that and it didn't go into it, then I would say on my calculator, okay, what's 3 to the 5th? Does 3 to the 5th divide into it? And I would just kind of guess and check my way up through. Okay. What is the fifth root of 32?
2.
2, because that's where it came from, was that it was 2 to the 5th. And we've got a fifth root of 24. And I know there's nothing more I can do with that, because 24 is already smaller than the smallest fifth root. Okay, 32 is as small as we can do. So I can't even check to see if anything else goes into 24 because it's already smaller than that. Over 4. One tiny little step to be done with this. What do we need to do to clean up our final answer?
Divide by 4.
Divide by that 4 only with the 2 on the outside. We can't divide the 24 because it's stuck under a root, but that 2 on the outside we can reduce out and get the fifth root of 24 over 2. Okay, so I warned you this is the longest type of problem we got going on here in this lesson today. So when we're simplifying a root of a fraction, separate it into root of top and root of bottom. Whatever kind of root it is, you need that many of them to cancel. So this was a 5th root, I need 5 of them. If it's a 4th root, you need 4 of them. If it's a 7th root, you need 7 of them. So you write out however many more you need to get it on up to that number. Multiply by the same things on the top, so we're really only multiplying by 1. Then multiply together all those numbers on the top. The 3, 4, 4, 4, 4. Multiply all those together and I get 5th root of 768 in this case. On the bottom, all your roots are going to cancel. That's why we did what we did, so that we would just get that number underneath. Then simplify your root by looking for any perfect roots that divide into it. Okay. All right. To balance out that longest problem in the assignment, here's the quickest problem in the assignment. In this problem, I have 6 to the 1/5. I actually have 7 of them. And I have another 6 to the 1/5, and I actually have 2 of them. So if I have 7 of them and 2 of them, how many of them do I have when I put them together? I have 9 of them. Okay, you can think of that power thing as like a variable, and we're kind of combining like terms here. We cannot multiply the 9 and the 6 because order of operations says that we have to do powers before we can do any multiplying. Remember, please excuse, we have to do powers in parentheses before we can do any multiplication. And so we can't multiply those together, and since the 5th root of 6 is not a nice number, we're just going to be done with it. This is not the cubed root of 14. That's the common wrong answer, common mistake that students make here, is to just subtract those numbers. We can only add and subtract roots if they are the same type of root. So these are both cube roots, that's good, but also of the same thing. So we cannot just add these together, subtract them together. It doesn't work that way. You can try it on a calculator and just see that we don't actually get the right answer. Okay.
But if they were both like the same number, you could?
If they were both the same root and the same number underneath, you could, but then you would actually just get 0, right? So it would be a little bit of a silly problem. But our goal is going to be to turn them into the same thing underneath, but then they'll probably have a coefficient attached to them. So to do that, we need to simplify the roots. So I'm going to simplify the cubed root of 16. To simplify a root, we're looking for a perfect, whatever kind of root it is, that goes into that number. So since this is a 3rd root, we're looking for a perfect 3rd or a perfect cube. 2 cubed is 8. 8 goes into 16. So I'm going to do cubed root of 8 times cubed root of 2. I'm just dealing with that 16 for now. What is the cubed root of 8? 2. So I get 2 cubed roots of 2. And then I'm going to bring this guy down minus a cubed root of 2. And there's really kind of like an invisible 1 in front of there, right? Because we can always say we have a coefficient of 1. So then if I have 2 of this minus 1 of this, how many do I have? 1 of it. So I have 1 cubed root of 2, or just a cubed root of 2. Okay, once we get the number underneath the root to match, then we can add or subtract the coefficients, the numbers in front of them. Just like we did on the last problem where we just added together the 7 and the 2. But we have to get it to be the same thing under the root and the same type of root. You cannot change, at least not easily or with skills that I'm going to teach you today, the type of root that it is. So that would already have to be the same. So we're really just trying to change the number underneath. All right, so that was all numbers. Now we're going to throw some letters in here.
Yeah.
When we simplify a cube root, we're looking for a perfect cube that goes into it. So we're looking for a perfect cube that goes into 125. Whenever I see things that end in 5, I start to think about 5s. So I'm going to check out 5 cubed. 5 times 5 times 5 is 125. So that means this cubed root of 125 is a perfect cube and gives us 5. Now for the variable part of it. We have the cubed root of y to the 6th. To evaluate this, I'm going to think about what we did yesterday, where we learned about powers and roots. So I could rewrite this, since it has a power and a root, as a fraction exponent. What would that exponent be?
6/3.
6/3. We learned top is power and bottom is root. So the top is going to be the power of 6 and the bottom is going to be the root of 3. What is 6/3? 2. So that whole thing just simplifies down to a y squared. You can divide a power by a root to simplify them. Okay, divide the power by the root. All right, this thing has a 1/2 power on the outside. We learned before when we had powers on the outside that we need to give them to everything inside. So I'm going to give it to the 9, then I need to give it to the u, and I have a power, and what do I do with those? I have a power to a power. What do I do with them? Multiply them. So that's just like before when we had like x squared cubed, we multiplied those. So I'm going to multiply 2 times 1/2 and I get 1. And for v, I get v to the 5th. Okay, we're almost done here. Our variables are good. 9 to the power of 1/2. Well, from what we did yesterday, top is power and bottom is root. So this is really asking for the square root of 9, which is 3. All right, simplifying the root with numbers and variables, we're going to take each part of it individually, each number, each letter individually. So this is kind of like problem number 7 that we already looked at. We were simplifying the root on that problem as well. The 5th root of 5 is not a nice number. A lot of students want to say it's 1, okay, but a root isn't doing a division. It's asking what do I multiply, in this case 5 times to get 5, and 1 times 1 times 1 times 1 times 1 is not 5, right? So a lot of students will want it to be 1, and I understand why, but it doesn't work that way. Then on number 7, we said when we're trying to reduce a variable that has a power and a root, what can we do to simplify those? Divide them. We want to do power divided by root. Okay. Power divided by root, we learned yesterday. So for a, I'm going to get a to the 1st. And that doesn't have a root anymore, so that's going to come out in front here. You don't have to write the 1. A first power is something that you don't have to write. I'm just writing it now. Now for b, we would say we have b to the 9/5. Well, that doesn't go unevenly, right? How many times does it go unevenly? 1. So I'm going to take 1 out. And how many are left over after I do that? 4. So I'm going to leave 4 stuck under. Okay, here we're thinking about remainders. So if I write it as 9/5, that's the same thing as 1 4/5. So I'm going to take the 1 out and leave the 4 in. For C, 13/5. How many times does 5 go into 13 evenly?
2.
2 times, so I'm going to take 2 out, which leaves how many in? 3 left in. And that is considered simplified. A lot of students struggle with this because it's longer than the problem started. And we kind of have a feeling that when we simplify things, it should be making the problem shorter, not longer. But the key to simplifying when we're dealing with roots is we want as little underneath the root as possible. Okay? And there is less stuff under the root than there used to be. Okay? Questions? All right, so this is a fraction one, similar to number 4, which I warned you is the longest problem, so this one we're going to expect to be a longer problem again as well. Okay. First thing we want to do when we have a root of a fraction is separate it. And there is some simplifying we could do on the bottom of that with the cubed root of y to the 7th. Just like we did in the last problem, we could divide the 3 into 7 and take some of that on the outside if we wanted to. I'm not going to bother doing that now. We're going to have to do simplifying at some point. We can either do it now or we can do it later, and it just doesn't really matter, so I'll just do it later. So I'm going to multiply this then by cubed root of y to the 7th. And cubed root of y to the 7th. Why did I do that? Because it's a cube root, so I need 3 of them. So there's 1 there, do 2 more, so I've got 3 of them. What do I do on the top?
Same thing.
Same exact thing, so I'm really only multiplying by 1. So now when I do all that multiplying on the top, I'm going to cube root. Underneath it, I'm going to have an x and y to the 14 because we're multiplying, and we learned that when we multiply, we add our exponents. So I've got 7 y's and 7 more y's. I've got 14 y's. On the bottom, what do I get?
Y to the 7th.
Y to the 7th. When we multiply 3 cube roots, they cancel to leave whatever was underneath. So since there was a y to the 7th underneath, that's what's left now. On the top, we have a little bit of simplifying we need to take care of. So like the previous problem, we can do our divisions. Well, we can't do anything with that x because there's only 1 x. How many times does 3 go into 14 evenly? 4 times evenly. So I'm going to take out a y to the 4th. And how many are left over after I do that? 2. Right, 3 goes in to 14 evenly 4 times, which makes 12. So there's 2 left over to be stuck underneath. Over y to the 7th. One more step to clean up our final answer is to do what?
Divide by y to the 7th.
Cancel out with that y to the 7th. So I can cancel out anything that's outside within there. So when I cancel out with that y to the 7th, on the top I'm still going to have my root. On the bottom I'm going to have
Third.
y to the 3rd because I canceled out 4 of them from the top. Questions? I have 5 square roots of y plus 6 square roots of y. So what do I have?
11 square roots of y.
11 square roots of y. Okay, that one's just a combining like terms problem. Last one, remember we cannot add and subtract roots unless they are the same, and these two are not. They have both cube roots, but there are different things under the roots. That means we need to simplify them and hope that in doing that, they end up matching. So in the first one, cubed root of 5 I can't do anything with. 3 divides into 5 for this x how many times? Evenly. 1 time evenly takes 1 x outside with how many leftovers? 2 left over. For the next one, to simplify cubed root of 40, when we simplify a root, we're looking for a perfect whatever kind of root it is that goes into it. So I start out at 2. 2 to the third is 8. Does 8 go into 40? Yes. So we're going to rewrite this as cubed root of 8 and cubed root of 5, and then I'll have that x squared there. Okay, separating that 40 into an 8 and 5 because 8 is a perfect cube and we'll be able to clean that up. What is the cubed root of 8?
2.
2. So I got a 2. I had the x out there. Can't do anything more with the 5. Can I do anything with the x squared? Why not?
Because it's only x squared and x cubed.
Okay, because 3 doesn't divide into 2. Okay, it doesn't divide in there, so we can't do anything to take any out there. Now, are the roots the same? They are both cube roots, and in them both we have 5x squared. So if I have 3x of them minus 2x of them, how many of them do I have? 1x of them. Questions? All right, your homework comes from 7.2 tonight. This is a difficult assignment. I know it is. It's a lot of properties. There are things that we learned before, but they're tricky when we put them all together, and the directions don't specifically tell you which property you're supposed to be using. So I know this is tricky stuff. Do your best with it, and we'll see how it goes tomorrow, all right?